This is Srikanth, Assistant Professor of Triple Department. In this session, I am discussing Norton's theorem. This Norton's theorem is used to find the load current in any circuit which is having more number of sources and resistors. So this is one of the powerful technique to calculate the load current. When we know the load current, we can calculate the voltage and power across the load. So that will be helpful to find all the parameters of load. First, let us go with the statement of Norton's theorem. Norton's theorem states that in any linear bilateral circuit which consists of voltage sources, current sources, and resistances can be replaced with a single current source in parallel with the resistance, where the value of resistance is the equivalent resistance between the load terminals by replacing the sources to 0, whereas voltage source is replaced with short circuit and current source is replaced with open circuit. And the value of current source is the short circuit current between the two terminals of the load. So we are going to calculate the short circuit current between the two terminals. Okay, simply we can say that in Norton's theorem, the circuit between the two terminals can be replaced with a single current source in parallel with the resistance. This is the way we are going to convert, which is having two current sources and one voltage source, and with resistors can be replaced with a single current source in parallel with the resistance. When we are having in parallel with the resistance, in order to calculate the load current, we are going to add the load resistance here. We are going to add the load resistance, and load current is equals to IL is equals to Norton's current into here we are going to use the current division rule. That is, whenever we want to calculate the current flowing through parallel branches elements, the current, whatever the current which is entering, is multiplied with opposite resistance divided by sum of two resistances connected in parallel. This is current division rule. So with this current division rule, we are going to calculate the load current in the load resistance. Now let us go with the steps to apply Norton's theorem. Now we are going to, in our first step, we are going to remove the load resistance. And where the load can be removed and make it as a open circuit between the two terminals A and B. And the second step is we need to calculate the open circuited equivalent resistance, that is called Norton's resistance Rn. We are going to calculate the equivalent resistance by making the sources to 0. That means voltage source is replaced with short circuit and current source replaced with open circuit. And then the next step, we are going to make the terminals, AB terminals, we are going to make it as a short circuit. We are going to make it as a short circuit, and we are going to calculate what is the current flowing through the short circuit terminals. That is nothing but the Norton's current. Short circuit current is nothing but the Norton's current as per the statement of Norton's theorem. And the next step is we need to draw the Norton's equivalent circuit by replacing the complete circuit with a single current source in parallel with the resistance. Here IN, which is connected in parallel with the RN. IN is the Norton's current, RN is the Norton's resistance. The next step, we are going to connect the load resistance. We are going to connect the load resistance. Whatever the load resistance we have removed, that load resistance is connected here in order to calculate the load current. Finally, we are going to calculate the current using current division rule. That is, IL is equals to IN into RN by RN plus RL. So these are the 6 steps we need to follow in order to calculate load current using Norton's theorem. Now we'll go with the example. Here we need to calculate the current flowing through the 40 ohm resistance using Norton's theorem. Here, which is given two voltage sources, one is 10 volt source and one is 20 volts source. One is 10 volt source and another is 20 volt source. And three resistors are given, 10 ohms, 20 ohms and 40 ohms. Now we are going to remove the 40 ohm resistance, remove the 40 ohm resistance, and we are going to calculate the equivalent resistance. We are going to calculate the equivalent resistance by making the sources to 0. So here we are making 10 volt source to 0, that is nothing but here we are having a voltage source only, so we are making both voltage sources as short circuit. Here you can clearly see these are short circuited. Now when these are short circuited and now we have opened the load resistance. So if you see from these terminals, from A and B terminals, these two resistors 10 ohms and 20 ohms are connected in parallel. So the equivalent resistance across A and B is, when the resistors are connected in parallel, the equivalent resistance is R1 R2 by R1 plus R2. So RAB is equals to RN, which is equals to 10 into 20 by 10 plus 20, which is equals to 6.67 ohms. Now, in order to calculate the Norton's current, we are going to make the AB terminals as short circuit, whatever the removed resistance terminals as short circuit, and we are going to calculate what is the current flowing through it. So here, this is the current which we need to calculate. So across the short circuit, the two currents are flowing. Let us consider the current flowing through. Current flowing from the 10 volts is I1. Current flowing through 20 ohms is I2. And these two currents are going in the same direction. So IN is equals to I1 plus I2. IN is equals to I1 plus I2. where I1 is equals to, here we are having only one voltage source in series with the resistance. So 10 by 10 is the I1 current, 10 by 10 plus, here also only one current is flowing. So 20 by 20, that is equals to 2 amperes. So this is the way we are going to calculate the Norton's current. Now, after calculating Norton's current and Norton's resistance, we need to replace the circuit with Norton's current source in parallel with the resistance. Here we are replacing a Norton's current, that is 2 ampere current source in parallel with 6.67 ohms. Now, what is our final output which is required? That is, we need to calculate what is the load current, what is the current flowing through 40 ohm resistance. So, in order to calculate the load current, we are going to use the current division rule. IL is equals to IN into opposite resistance is 6.67 divided by 6.67 plus 40, which is equals to 0.286 amperes. And the next problem is we need to calculate the current flowing through 3 ohm resistor using Norton's theorem. So here we need to calculate current flowing through 3 ohm resistance with the Norton's theorem. So in order to calculate the Rn, in order to calculate the Norton's resistance, what we have to do? We have to replace the sources with 0, that is voltage source replaced with short circuit and current source replaced with open circuit. So, and we need to open circuit the load terminals. So after doing this, the circuit will become, here we have open circuited the load resistance, and here it is the voltage source is short circuited. Voltage source is short circuited. So when you see between these terminals are equivalent, we need to calculate. When we are calculating the R equivalent, if you see from these two terminals, this 4 ohms and 5 ohms are connected in parallel. And when we take the 4 ohms and 5 ohms connected in parallel, R equivalent 1 is equals to 4 into 5 by 4 plus 5, which is equals to 2.22 ohms. So R equivalent 1 we got it as 2.22 ohms, and now we are replacing the resistance, these two resistors, with a single resistor, that is 2.22 ohms, that is in series with the, that is connected to the 2 ohm resistance. Now if you see from these two terminals, Rn value we are going to get it as, these two are in series, 2 plus 2.22, which is equals to 4.22 ohms. Now we got the Rn value. Next we need to calculate In value. So for calculating In, we are going to make the short circuit across the two terminals, and after short circuiting, here we have got two loops, that is with current I1 with current I2. So I2 is nothing but the In. So if we write the KVL, if we write KVL in loop 1, KVL in loop 1, here the current is entering the negative terminal, so minus 20 plus 4 into I1 plus 5 into I1 minus I2, that we can consider it as In because these two are same. So here 4 plus 5, 9 I1 plus 9 I1 minus 5 IN is equals to 20. This is our equation number 1. Now KVL in loop 2, KVL in loop 2, that is equals to, here only two resistors are there, so 5 ohms and 2 ohms. So 5 into I2 minus I1 plus 2 into I2. Not, let us consider this I2 as IN, which is equals to 0. That is equals to minus 5 I1 plus 7 IN is equals to 0. This is our equation number 2. So if we solve these two equations, we are going to get the I1 value as 3.684 amperes and IN value as 2.631 amperes. So we got the I1 value and IN value, and here now we got the IN value. Now we are going to replace the circuit with a current source in parallel with the resistance. A current source in parallel with the resistance, that is 2.631 amperes. And what is the resistance we got? 4.22 ohms. This is the equivalent, Norton's equivalent between the terminals A and B. Now we need to calculate what is the current flowing through 3 ohm resistance. For that we are going to add 3 ohm resistance to this Norton's equivalent. Here we are going to add the 3 ohm resistance to this Norton's equivalent in order to calculate the load current, where I 3 ohms is equals to IN into opposite resistance is RN by RN plus RL, that is equals to 2.631 into 4.22 by 4.22 plus 3, which is equals to I 3 ohms is equals to 1.538 amperes. Now we need to calculate the Norton's equivalent for the given circuit. Here for this circuit, Norton's equivalent, we need to calculate between A and B terminals. So here, in order to calculate the Norton's equivalent, first it is already open circuited terminals are given. So for calculating Norton's equivalent resistance, we need to replace the voltage source with short circuit and current source with open circuit. Now I am making it as a short circuit. Once it is short circuited, now our circuit will become like this, and here it is open circuited current source. This is 5 ohms, 20 ohms and 4 ohms. These are the AB terminals, RAB, which is equals to RN. So here, in order to calculate the Norton's resistance, we have to see the circuit from the AB terminals, and we have to start reducing from the other end, that is from the 5 ohms and 20 ohms. Here if you see these two resistors, 5 ohms and 20 ohms, these two resistors carries a different current and they are connected between the same two terminals. So we can say that these two resistors 20 ohms and 5 ohms are connected in parallel. So 20 ohms and 5 ohms are connected in parallel. Connected in parallel. When these two resistors are connected in parallel, so R equivalent 1 is equals to 20 into 5 by 20 plus 5, which is equals to 100 by 25, which is equals to 4 ohms. Now we got the R equivalent 1 as 4 ohms. So our circuit will become, that is 4 ohms and 4 ohms. A, B terminals. So RAB is equals to, if you see this between these two terminals, these 4 ohms and 4 ohms are connected in series. When the resistors are connected in series, which is the equivalent resistance is R1 plus R2, that is equals to 4 plus 4, 8 ohms. 4 plus 4, which is equals to 8 ohms. Now we got the RAB value. And then we need to calculate what is the short circuit current, that is Norton's current. So for that we need to replace the open circuited terminals with short circuit. Here I'm redrawing the circuit. Here we are making it as short circuit. That current we need to calculate 4 ohms, 3 amperes, 25 volts, 5 ohms and 20 ohms. This is our circuit. Now we need to calculate Norton's current. So in order to calculate the Norton's current, either we have to go with mesh analysis or nodal analysis. So here if we go with mesh, we have to go with 3 loop mesh equations. If you go with nodal method, a single node is enough. Single nodal equation is enough to calculate the Norton's current. So we'll go with the nodal analysis. That is V1 with 0 volts we are taking, only one node we are having. So if we write the KCL at node 1, KCL at node 1, let us consider the node 1 voltage as V1. Here in the nodal analysis, whenever we are writing the KCL, we are going to assume that all the currents are leaving from the node. All the currents are leaving from the node. So here the current flowing through 5 ohms is V1 minus 25 by 5 plus V1 minus 0 by 20. Current flowing through 20 ohms. And current flowing through 3 amperes is, our assumption is away from the node, but the current source which is coming is towards the node, that is minus 3 plus V1 by 4, which is equals to 0. So here if we take V1 common, 1 by 5 plus 1 by 20 plus 1 by 4, which is equals to 25 by 5, 5 plus 3, 8. So here we are going to get V1 into 0.5, which is equals to 8, where V1 is equals to 16 volts. Now we got the V1 value as 16 volts. V1 value as 16 volts. When we got V1 value as 16 volts, IN value is equals to what is the current flowing through? 4 ohm. What is the current flowing through 4 ohms? V1 minus 0 by 4. That is equals to 16 minus 0 by 4, which is equals to 4 amperes. This is the Norton's current we got. Already we have calculated Norton's current and Norton's resistance. Now we are going to replace the circuit with Norton's current source in parallel with the resistance. This is the Norton's resistance. We got it as 8 ohms. Norton's resistance, we got it as 8 ohms. And Norton's current, we got it as 4 amperes. This is the way we are going to get the Norton's equivalent between the terminals A and B. Now, here also we need to calculate the Norton's equivalent between the terminals A and B. So, in order to calculate Norton's equivalent between A and B terminals, first we need to calculate Norton's resistance. So, for Norton's resistance, this is the current source. We have to open circuit this current source and short circuit the voltage source. When this current source is open circuited, our circuit will become like this. Now, so here 4 ohms, 8 ohms, 5 ohms, 8 ohms. We need to calculate RAB, that is nothing but Norton resistance. So, in order to calculate the RAB, if you see the resistances from these two terminals, this 8 ohms, 4 ohms and 8 ohms are connected in series. That is, R equivalent 1 is equals to 8 plus 4 plus 8, that is equals to 20 ohms. Now I am replacing the circuit with the equivalent resistance. That is 20 ohms, 5 ohms, and we need to calculate AB. What is the RN or RAB? So if you see between these two terminals, this 5 ohms and 20 ohms are connected in parallel. So RAB is equals to R1 R2 by R1 plus R2. 20 into 5 by 20 plus 5, that is equals to 100 by 25, which is equals to 4 ohms. This is the Rn value. This is the Norton's resistance value. Now we need to calculate Norton's current. So for that we need to replace the circuit with short circuit. Between the two terminals we are making to make short circuit. Let me draw the circuit first. Here we need to calculate Norton resistance, so Norton's current 8 ohms, 4 ohms, 5 ohms. Here the source value is 2 amperes, 12 volts. 12 volts. So here we need to calculate the Norton's current. When we want to calculate the Norton's current, we are making it as short circuit. Once there is a short circuit between the two terminals and only one resistance is connected between the two terminals, then that resistance will become a short circuit, because when the two resistors are connected in parallel, the equivalent resistance will be R1 R2 by R1 plus R2. So here we are having one resistance is 5 ohms. The short circuit resistance is 0 ohms. If we calculate the equivalent resistance, R1 into RSC by R1 plus RSC. So we are going to get the R equivalent value as 0. So this 5 ohms can be replaced with a short circuit. Okay. So this 5 ohms resistance is replaced with a short circuit, and here we are going to calculate the what is the current flowing through this particular short circuit. So here we are going to apply the nodal analysis again. So if we apply KCL at node 1, minus 2 amperes, because current is entering towards the node, but our assumption is leaving from the node. Minus 2 plus V1 minus 12 by 4 plus V1 minus 0 by 8, which is equals to 0. Here if we take V1 common, 1 by 4 plus 1 by 8, which is equals to 3 plus 2, which is 5. V1 is equals to 5 by 0.375, which is equals to 13.33 volts. Now we got it as V1 value as 13.33. So IN is equals to V1 by 13.33, which is equals to, sorry, V1 by 8, V1 by 8 1.66 amperes. So we got IN value and RN value. So our circuit can be replaced with the equivalent Norton's circuit, that is 1.66 amperes, and Rn we got it as 4 ohms. So this is the Norton's equivalent between AB terminals. So this is the way we have to calculate Norton's equivalent. With this we can easily calculate the load current, and this is the most powerful technique to calculate the current flowing through any element in the given circuit. In this session we have discussed what is the statement of Norton's theorem and what is the procedure and some examples. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.